Hi everyone, I hope you all are doing well during this quarantine period. We have already finished with biomolecules and now we are going to start with a new chapter. Before starting with the new chapter, I would like to ask you one thing is we all are familiar with mixtures. We know that when two or more substances combine together, it forms a mixture. If you recollect the first chapter of Standard 11, Basic Concepts of Chemistry, you will remember that we had studied mixtures were of two types, homogeneous mixtures and heterogeneous mixtures. Now I have mentioned the examples for both, that is for homogeneous and heterogeneous mixture. For homogeneous mixture it is alcohol and water, whereas for heterogeneous mixture it is oil and water. Now we know that homogeneous mixtures they are in single phase and heterogeneous mixtures they are in two phases. Now what does that mean? For example, if we are taking the example of homogeneous mixture, that is water and alcohol. So if you are mixing water and alcohol, you won't be able to figure out where are the molecules of alcohol and where are the molecules of water. Both the substances are going to mix in such a way that it is going to appear as a solution, that is, or you can say it is going to appear in a single phase. Now if you move on to heterogeneous mixtures, you will see that when you mix both the substances, you can differentiate the two substances very well. For example, if you are mixing oil and water, even after mixing it vigorously, the two layers they separate out, right? So you can see the two phases in there. That is why it is an example of heterogeneous mixture. Here is one more example of homogeneous and heterogeneous mixture. As you can see, an example of cold coffee is placed under homogeneous mixture, because if you look at the cold coffee, you cannot figure out where is the coffee, milk, water, sugar, ice cream, etc. It appears in one phase. That is why it is an example under homogeneous mixture. If you look at the second one, the example for heterogeneous mixture, it is a combination of fruit salad, or you can say combination of fruits into a fruit salad. So you can easily pick out the grapes, the orange, strawberry, etc. So that is why it comes under heterogeneous mixture. In this chapter, specifically we will be studying about homogeneous mixtures, the mixtures which appear to be or are in one phase. Now homogeneous mixtures, they are classified based on the size of particles. Like we know each and every substance is going to have a different sized particle. So they behave as colloids or as true solutions. But in this chapter we will be studying about true solutions. Now we know that solutions they are formed when two or more pure substances combine together, right? So we know that solution is a combination of solute and solvent. Solute is the smaller part and solvent is the bigger part of the solution. For example, if you look at the body fluids that are present in our body, even they come under solution. Apart from that, you have a lot of examples of solution. We know that the solutions they are formed by mixing of a solid into liquid or liquid into liquid, but actually the state of the solute and solvent could be any of the three states, that is it can be a solid, liquid or gas. So based on the state of solute and solvent, there are 9 types of solution. So let us study which are these 9 types of solution. Here if you look, the first column is the state of solute, the second column is the state of solvent, and then example of each type of solution is given. Now we move on to the first type of solution, where the smaller part of the solution is solid and the larger part is liquid. That is, solute is solid and the solvent is liquid, right? So the examples that they have given is seawater, benzoic acid in benzene. So seawater we know salt and water. So salt is going to be solute and water which is in large quantity will be the solvent. Similarly, benzoic acid in benzene. Then you have sugar in water. So sugar is going to be the solute and water is going to be the solvent which is in liquid phase. Next, the solute and the solvent both are in solid state. The example that they have given here is metal alloys such as brass and bronze. We know that alloys, they are a combination of a metal with a non-metal, right? So brass and bronze both are a combination. Now, brass is a combination of copper and zinc, and bronze is a combination of copper with any other metal. So both are in solid state, whether it is going to be your solute or solvent. Now next one is solid and gas. So solid is going to be your solute and gas is going to be the solvent. So iodine in air, iodine is in solid state and gas is the solvent one. So iodine in air. Now we move on to the next group. We start with the liquid now. So the first one, solute and solvent both are in liquid phase. So example is gasoline and ethanol in water. Okay, so ethanol and water both are in liquid phase. Gasoline, it is derived from petrol, and it is used as fuel to run engines. Next is solute is in liquid state and solid is in the solvent state. An example they have given is of amalgams of mercury with metals as mercury in silver. Now what is the meaning of that word amalgams? Amalgams means mixture of metal with some other metal. So example also they have given mercury in silver. Next one, liquid phase is solute and gas phase is solvent. An example is chloroform in nitrogen. Of course, chloroform is in liquid state and nitrogen is in gaseous state. We will move on to the next set now. We start with the gases now. So here the solute is gas and solvent is going to be liquid. So example is carbonated water. For example, soda that we drink. So carbon dioxide of course is going to be gas and liquid. Water is more in that. So it is going to be a combination of gas and liquid. The next one is gas and solid. Hydrogen in palladium. Here hydrogen is gas and palladium is going to be in solid state. Hydrogen, so gas will be in smaller amount, and palladium, which is solid, that will be in more amount. The last one is gas and gas, where your solute and solvent both act as in, or they are in gaseous phase. So common one or a common example is air, because it's a mixture of air. So oxygen, nitrogen, argon and other gases. Chemists, they are always eager to know the capacity of solution to dissolve the solute. Okay, for example, if we take a solute and add it in a solvent, it is going to dissolve readily and form the solution. But if we go on adding more solute, what is going to happen? The rate of dissolution, that is the mixing of solute and solvent to form solution, is going to decrease. Why is that so? Because the capacity of solvent to take the solute molecule is going to be filled up, or you can say in other words, it is going to be saturated. For example, I think I have already explained you this in 11th standard. If you take sugar and if you add in water, then it is going to dissolve. Here sugar is going to be the solute and water is going to be the solvent. If I keep on adding that sugar again and again, a time is going to come when the water is going to be completely filled with that solute, that is sugar. So after adding more sugar, what is going to happen? That sugar is going to start out crystallizing. And what is the reason for that? Because the solution becomes saturated. And I hope you know what is the meaning of saturated. The capacity is full, and even if you try to put in something there, it is not going to take in. Here an equilibrium is achieved. Now how is this equilibrium achieved? First, dissolution takes place, that is you are using solute and solvent, both are mixing and giving your solution. Now if the amount of solute becomes more, okay, then the solution becomes saturated. This is the point when it starts crystallizing out. So how is this equilibrium attended? Uh, the number of solute molecules leaving the crystal into the solution becomes equal to the number of molecules returning from the solution to the crystal. I will explain you this with the example pertaining to sugar and water. So when will be the equilibrium attained? Like the sugar crystals, the molecules will come out from the sugar crystals, they will mix up with water. That process is solution. And when the molecules again form the crystal, that is when your crystallization is going to take place. Now, depending upon the capacity of the solution, there are three types of solution. The first one is the unsaturated solution, second saturated solution, and the third one supersaturated solution. By now you know what is the meaning of saturated solution. Saturated solution means whatever substance you are going to add more, or more solute you are going to add, and if the capacity of solvent is full, it is going to crystallize out. Okay, the first one is unsaturated solution. Unsaturated solution means less number of solute when you compare it with that of the solvent. Here the solute molecules will be less when you compare with that of the solvent molecules. The second one is saturated solution, which you already know. The third one is supersaturated solution. So in this, the equilibrium amount of solute is very much high when you compare with that of the solvent, and that is why it is called as supersaturated solution. So the amount of solute is going to be very high when you are going to compare it with the solvent. Now we move on to the next concept, that is solubility. So the definition for solubility is amount per unit volume of saturated solution at specific temperature. And this solubility is measured in terms of concentration unit, that is mole L raised to -1, or you can say mole L inverse. Now we are going to study the factors affecting solubility. So there are a number of factors that affect solubility, like the nature of solute, the nature of solvent, temperature, pressure, etc. Okay, so under this, the first one that we are going to start it with nature of solute and solvent. It is usually observed that chemical substances which have similar chemical properties, they tend to mix with each other readily. Okay, and if you compare substances which have different chemical properties, then there comes little problem when it comes to mixing. Now why does this happen? Because substances with similar chemical properties, they are going to have similar intermolecular force of attraction. That is why they mix with each other properly. There goes a saying that like dissolves like. So this is what solubility follows. You will also see that polar solutes, they dissolve only in polar solvents. Why? Because we know polar as in they are going to have plus and minus charge present on it. Now observe our own life. When we go to college or when we go to school, we come across so many students out there. Okay, but you have that one best friend or two best friends. Now why is that so? Because when you come across a person who is having similar hobbies, likes, dislikes like you tend to be more friendly with that person. Okay, so similarly is the case of solubility. Like dissolves like. One example is mentioned under the nature of solute and solvent, that is of NaCl and water. We know that when NaCl is going to split up, it is going to give you Na plus and Cl minus, and when water is going to split up, it is going to be H plus plus OH minus. But there we know that H has a plus charge and O is the electronegative element there. Right now in this picture, if you see, Cl is having a negative charge. That is why the H atoms of the water are getting attracted to it. If you look in the next diagram, Na is plus, sodium is plus. That is why the oxygen electronegative element is getting attracted to Na. Here there are strong ion dipole interactions of Na and Cl, which is going to facilitate the hydrogen bonding between them. Okay. So this is one example that is mentioned here. Now prior also I told you polar solutes will dissolve only in polar solvents and non-polar solutes will dissolve only in non-polar solvents. So again remember, under nature of solute and solvent, like dissolves like. Now there is this one question that is asked in your textbook: why naphthalene dissolves in benzene but not in water? And what is the answer for this? Benzene is going to be a non-polar solvent. Okay, naphthalene is non-polar, right? So naphthalene is going to dissolve in benzene because it is non-polar, but water is polar because it is having plus and minus sign. That is why naphthalene is not going to dissolve in water. Okay, I hope you know what is the meaning of polar and non-polar. Polar means it is going to have plus and minus sign, and non-polar, both the signs are going to be similar, either plus plus or minus minus. Next factor is the effect of temperature on solubility. Okay, here the solubility of a substance changes with temperature, which depends on the enthalpy of a solution. We know that enthalpy is nothing but heat. So there are two types of reactions we know. One is the endothermic reaction and the next one is the exothermic reaction. The endothermic reaction is where heat is absorbed from the surrounding, and exothermic reaction means heat is given from the system. Now if you look at the pictures there, first one is an ice cream cone. So there you can see, because that ice cream is absorbing heat from the surrounding, it is melting, so it is endothermic. Next is bonfire. So there, because of that fire, heat is given out, so it comes under exothermic reaction. Now under the effect of temperature on solubility, they have explained it with the example of KCl, and for exothermic they have explained it in terms of lithium sulfate. Now dissolving of KCl in water is an example of endothermic reaction. Why? Because this KCl is going to absorb heat from the surrounding and then it is going to get dissolved in water. Okay, now this is based on Le-Chatelier's principle. That is, when you apply heat to a system, stress is produced on that system. Okay, so that is what, because it is absorbing heat, it comes under endothermic reaction. When you move on to exothermic reaction, it is the example of lithium sulfate. So lithium sulfate, it is going to dissolve in water, but it is going to give out heat. So the solubility of the substance is going to decrease with increase in temperature for exothermic process. Here is a graph which shows the variation of solubilities of ionic solids with temperature. Okay, the first one under that, if you look at the x-axis, then it is the temperature and y-axis is the solubility. So if you look at the first point, it says that solubility of sodium bromide, NaCl and KCl change slightly with temperature. So if you look at the increase, then very slightly it is increasing. Whereas if you look at the solubilities of KNO3, that is potassium nitrate, sodium nitrate and KBr, it increases with a very good amount with the temperature. And solubility of Na2SO4 decreases with increase of temperature. It is not shown in that diagram, but of course the graph is going to go downwards. Okay, now the solubility of gases in water is usually decreases with increase of temperature. So if you are going to mix a gas in water and if you are increasing the temperature, means you are applying heat. So what is going to happen? So when the gas is going to start dissolving in water, the gas molecules in the liquid phase, they get condensed. Okay, and the condensation is an exothermic process, that because heat is getting or it is given out, and the solubility of gases in water, it is going to decrease when the temperature is raised. When you are raising the temperature, that means you are heating the particular system. The third factor is effect of pressure on solubility. Now if we look at solids and liquids, then their solubility is not affected by pressure. Why is that so? Because it is difficult to compress solids and liquids. Liquids to some extent you can compress, but when you come to gases, then the solubility of gases are highly affected by pressure. The solubility of gases increase with increase in pressure. Effect of pressure on solubility is explained with the law which is called as Henry's law. Now, this law states that the solubility of a gas in a liquid is directly proportional to the pressure of the gas over the solution. So, if you look at the equation down there, S is the solubility and it is directly proportional to the pressure. I told you if you want to remove that proportionality sign and put a constant, you will have to put a equal to sign there. So, that becomes S is equal to KHP. Now what is that KHP? That is the proportionality constant for Henry's law constant. Now S there is the solubility of the gas in mole liter raised to -1. I told you solubility is measured in concentration terms, that is mole L inverse. P is the pressure and it is measured in terms of bar. Okay, if you want to find the units of Henry's law constant, or you can say the proportionality constant, then you are going to write it as S by P, where S stands for solubility and P is the pressure. Then after that you have to mention their units, that is solubility is mole L inverse and pressure is bar. So if you want to write the units, you can even write it as mole L inverse bar inverse. Now why bar becomes inverse? Because it is from denominator, it is going in the numerator. Okay, now if you are taking pressure as 1 bar, then your proportionality constant will become KH is equal to S, because S upon 1 is going to give you S. Thus KH is the solubility of a gas in a liquid when its pressure over the solution is 1 bar. I hope you understood how did you get KH is equal to S, because if you are taking pressure is equal to 1, then the equation will become KH is equal to S upon 1, which will give you KH is equal to S. Henry, he demonstrated an experiment to show the effect of pressure on solubility. Now what did he do is, he took a soft drink which was carbonated, for example our Sprite or Coke. So what did he do is, he created a mixture of gases in there and a lot of pressure was exerted because of that. Now for example, if you get a Coke bottle, okay, and if you shake it vigorously, what happens there? The carbon dioxide that is present in the soft drink, it comes up to that area where the place is vacant, and because that carbon dioxide comes up, it exerts pressure on the wall of the bottle. But we know that more amount of carbon dioxide has already dissolved in the soft drink. So when you open the cap of the bottle, you will see that the excess of carbon dioxide, it pops out, as you can see in the picture here.